Okay, we're going to talk about a class of problems where you're asked to find the sign of the divergence of curl. And you're going to use a vector field plot and Green's theorem. So just why we're using Green's theorem again? Isn't it just that qx plus p minus py thing? Actually, remember that we can rewrite Green's theorem in a fancier way using our curl. That was where we actually got the curl from. We just kind of pulled it from nowhere. And so now we're basically being asked to find the sign of these line integrals. Really, that's actually the definition of the curl and the divergence. So basically, if you find this, if this thing, for example, is positive, this integral, then for c sufficiently small, it'll actually imply that this thing is positive too. And similarly, for example, if we show that this line integral is negative, and the curve is small, this will actually be small as well. And we're looking at small curves. So you don't actually need to look at small curves. You can just use whatever curve you like in these problems because it's very symmetric. So let me just give an example of what I'm talking about. So let's consider a vector field of this form, and please bear with me as I attempt to use my non-existent artistic skills. So it'll be a radial vector field, and it'll be smaller near the origin, and it will get bigger as we get outside. So how do we find the divergence and the curl? So what we need is a curve. Use the symmetry of the problem. So, for example, don't use a square for this. Don't use a square-shaped curve. I would use an annulus, semicircular arcs. Right, because we have some nice circular symmetry going on here. So let's draw these let's draw these annuli. And in fact, for Green's theorem, we want positively oriented curves. So which means counterclockwise, remember. So I'm going to indicate these with the arrows. And remember, the second Green's theorem, and just to recall where that came from, we took the original Green's theorem. We flipped the sign and the spot of the vector field, and this ended up changing the tangent vector to a normal vector. That's just where that comes from. So the tangent vectors of the curve, they'll be along these streamlines. So actually, this arrow, it actually points in the direction of the tangent vector, t. But on the other hand, if you want to draw the normal vector, let's just draw something orthogonal to this curve. This is n. This is n. This is n. Remember, n is actually outer normal. And finally, this is n over here too. So I'm drawing n because remember we have an n in a Green's theorem. So we have now enough information to see. Oh, and these vector fields are for some f, right? So now we have enough information to see what the sign of this line integral is. So obviously we have 4 pieces. So why don't we break this up into 4 curves? 1, 2, 3, and 4. And I'm going to make a table just to organize what my thoughts are on each curve. So for the first curve, what do we see? We see f dot n. Remember, that's what we want for the divergence. F dot n, f is pointing to the right and it's pointing down. This is 0. And this is actually the same case for 3. So what do we have for the next curve? For 2, the normal vector is pointing outwards and f is pointing outwards. So actually it is positive. And notice it's actually for big magnitudes. So remember, this is big on the outside and it's small on the inside because, for example, our vector field could be just R. That's a nice model for what this is. So on the other hand, for curve 4, it's negative, right? Because the normal is pointing inwards, but the f is pointing outwards. So their dot product is negative, but notice it is small magnitudes. So the divergence is big minus small. So this is positive. So we conclude from this idea that the divergence of f should be positive. We just looked at a single curve, but because of the symmetry of the problem, this is good enough to argue. Oh, okay, let me say it like this. The problem is artificial enough that you don't need to use small curves. It's designed in such a way that you only need to use curves that look like this. So we found it for one curve. It should be true for all of them. So let's do the curl now. So if we look at f dot dr, or f dot the tangent vector, however you like, f is pointing to the right for curve 1, and dr is also pointing to the right, so this is actually positive. And for curve 2, f is pointing tangentially. This is actually in the theta direction, whereas the normal vector is pointing outwards in the the r direction. So really this is just 0. The dot product should be 0, clearly. And this will actually be the same thing for curve 4. So the only tricky one is curve 3. It's actually, remember, the tangent vector is pointing downwards, and f is pointing upwards. So actually the dot product is negative here. And it's actually, notice it's the same magnitude by symmetry. Right, because if, for example, if f is r, surely the magnitude does not depend on the direction. So therefore, for the curl, it'll be equal to a positive plus a negative of the same size, so it'll be 0. So therefore, the curl of the vector field should be 0, and it will not have a sign. Okay, let's do another example. We'll now do one that looks more rectangular. So instead, I'm going to have a vector field that's just pointing upwards. It will look big at the bottom. It will get smaller as we move up. So like one example you could think of is f equals 0. Notice how all these point up, and you could think of minus y or something like this. Because this gets smaller as we increase y. So let's make our table again. And of course, we need a curve. So I say let's draw a curve from the top to the bottom, like so. Again, we're using the symmetry. We don't want to draw a circle here. We want to draw something rectangular. Again, I'm doing positively oriented, so it should be counterclockwise. So I might again also draw the normal. Outward unit normal, again. And so now we have enough information to compute the line integral of these curves. So for the first curve, what do you think the integral should be for the divergence? I think f dot n, f is pointing up, n is pointing down. This should be less than 0. Moreover, for the magnitude, I'm going to say big, right? Because our vector field is biggest at the bottom. Whereas if we go up to curve 3, notice it is small. And if we want the sign, notice they're both pointing up, so it's actually positive. So what about curves 2 and 4? Well, n is pointing right. The vector field is pointing up, so the dot product should be 0. And similarly with curve 4, where we have left and up. So let's compute the divergence. The divergence will be, it'll be minus big plus small, so this will be less than 0. So the divergence of f should be less than 0. And clearly, if we compute the divergence of 0 minus y, this is just negative 1. So that's consistent. So let's do the curl now. So if we do f dot dr, or f dot t, well, for curve 1, dr is pointing to the right, f is pointing up, so dot product is 0. And we get something similar with curve 3. So really, we just have to look at curves 2 and 4. So for curves 2 and 4, f is pointing up, and our curve is pointing up. So actually, it's positive. And on the other hand, if we go to curve 4, our curve is pointing down, and f is pointing up. So actually, the dot product is negative in this case. And moreover, by symmetry, look at the magnitudes of, for example, these two lines. It is the same magnitude. That says magnitude. So it is positive plus negative of the same sign. In other words, the same coefficient. So it should be 0. The curl of f is 0. And if we, for example, if we computed the curl of 0 minus y, in 2D, it just looks like qx minus py. That certainly will be 0 because this is q, this is p. So it's consistent. Yeah, so I think if you follow this procedure, then this should help you with this kind of problem. Thanks for watching.